You stand on the waterfront, watching a cruise ship glide out of the harbour. Its gleaming white hull towers like a 20-story building. 18 decks, a length of 362 meters. On board, there are 6,700 passengers and 2,400 crew members. Swimming pools, restaurants, theatres, casinos, an ice rink, an amusement park. A floating city that will soon venture into the open ocean for a week. From the outside, it resembles a colossal floating hotel. Beautiful, luxurious, and a bit absurd. 9,000 people aboard a ship in the middle of the sea. But here's what most people don't realize. A cruise ship is not just a hotel on water. It is one of the most complex engineering systems on the planet. Every element of this system, from the height of the superstructure to the depth of the keel, from the power of the engines to the width of the corridors, from the number of lifeboats to the temperature of the air conditioning, is the result of a rigorous collision of physics, medicine, psychology, economics, and maritime law. Because a cruise ship must solve a problem that no other vessel faces. It must be both a safe ship and a comfortable city. And these two requirements are in a constant, unyielding conflict. Make the ship more stable, and it will sway more violently, leaving passengers to endure seasickness in their cabins. Make it softer, and you risk losing stability in a storm. Raise the superstructure higher, more cabins, more revenue. But the sail area increases, making the ship unmanageable in strong winds. Add more steel bulkheads, safer in case of flooding, but passenger spaces turn into a maze of dead ends, making evacuation impossible. Every decision is a precarious balance, and behind this balance lies not just money, but lives. Today, we will uncover the engineering secrets of a cruise ship, what lies beneath the waterline, behind the cabin walls, and within systems that passengers are blissfully unaware of, and why each of these secrets is a compromise that determines whether the ship will return to port. Let's start with the most obvious question that, for some reason, few people ask. How does a cruise ship not capsize? Look at its silhouette, a narrow hull. Above it, a massive superstructure stretching almost the entire length, as wide as the hull, rising 15 to 18 decks high. The center of gravity of this structure is high, very high, significantly higher than that of any cargo ship, tanker, or bulk carrier. A high center of gravity is the enemy of stability. The higher the center of gravity, the lower the metacentric height, the distance between the center of gravity and the metacenter, which determines whether the ship will return to an upright position after tilting. A tanker might have a metacentric height of 3 to 5 meters. A cruise ship often has less than 2. Sometimes it's around 1 meter. The corridor between stability and capsizing is as narrow as a razor's edge. How do engineers tackle this problem? In several ways, simultaneously. First, a heavy bottom. Everything that has significant mass and can be placed low is positioned at the bottom. Engines, generators, fuel tanks, water treatment systems, ballast tanks, all of these are located in the lowest part of the hull. Thousands of tons of steel and machinery, lowered as far down as possible, create a counterbalance to the towering superstructure. Second, a lightweight top. The superstructure of a cruise ship is not a monolithic steel construction. The upper decks are built from aluminium alloys, which are 3 times lighter than steel, while maintaining comparable strength. Every ton saved up top is a ton that doesn't need to be compensated for with ballast below. Every ton translates to millimeters of metacentric height. The third aspect is width. Modern cruise ships are disproportionately wide for their length. Take the Oasis class from Royal Caribbean, for instance, 362 meters long and 66 meters wide. This gives a length-to-width ratio of less than 6. In comparison, a container ship typically has a ratio of 7 to 8, while a military vessel ranges from 9 to 10. A wider hull enhances initial stability by increasing the moment of inertia at the waterline. However, this wider design also results in greater water resistance, higher fuel consumption, and reduced speed. It's a trade-off. But this raises a question. If the metacentric height of a cruise liner is already low, why not increase it further by loading ballast into the hull? Lower the center of gravity as much as possible to make the ship nearly impossible to capsize. Here, the physics of comfort starts to push back. A greater metacentric height leads to a shorter period of rolling. A ship that quickly returns to an upright position rolls sharply, with high angular accelerations. For cargo, this is problematic. Containers can break free from their restraints. For passengers, it's catastrophic. Such abrupt rolling can induce seasickness in most travelers within hours. Nausea, dizziness, and a complete loss of functionality ensue. A cruise ship with 6,000 passengers incapacitated by seasickness is not just uncomfortable, it's a business disaster. The ideal rolling period for passenger comfort is around 25 to 30 seconds. A slow, gentle sway that most people hardly notice. To achieve this, the metacentric height must be relatively modest, sufficient for safety, but no more. This is the narrow corridor, stable enough to avoid capsizing in a storm, yet gentle enough to spare passengers from being jostled about. However, even the optimal metacentric height cannot fully shield against ocean waves. This is where a system comes into play that passengers are often unaware of, yet it significantly influences their comfort more than the size of the pool or the quality of the buffet. Stabilizers. Retractable underwater wings, steel fins several meters long, are installed on either side below the waterline. They function like ailerons on an airplane wing. When the ship begins to tilt to the right, sensors detect the shift, and a computer calculates the necessary angle in a fraction of a second, adjusting the fins to create a hydrodynamic force that counteracts the tilt. The left fin rises while the right fin descends. The ship levels out before passengers even notice the lean. Modern active stabilizers can reduce rolling by 80 to 90%. That's a staggering figure. Without stabilizers, the tilt in moderate waves could reach 15 to 20 degrees. With stabilizers, it's reduced to 2 or 3. This makes all the difference between a comfortable evening in the dining room and evacuating dishes from the floor. However, stabilizers only function while the ship is in motion. The hydrodynamic force is proportional to the square of the speed. An anchored ship is defenseless against rolling. This is why cruise liners rarely anchor in open water. They are either docked or underway. Now let's delve into what lies beneath the waterline, information that no brochure will ever reveal. A cruise ship generates as much waste as a small town, every single day. 9,000 people on board consume food, drink water, take showers, use restrooms, do laundry, and generate trash. The daily volume of wastewater amounts to hundreds of thousands of liters. Food waste totals tons. Solid waste also reaches tons. Used oil, chemicals from pools, photo labs, laundries, and medical centers. Where does all of this go in the middle of the ocean? Inside the hull, on the lower decks, lies an entire industrial infrastructure. Wastewater treatment systems, membrane bioreactors, purify water to a quality that meets international standards for discharge into the sea. Incinerators burn solid waste at temperatures exceeding 850 degrees Celsius. Oil-water separators, centrifuges, extract oil and fuel from water, ensuring that not a single drop of hydrocarbons escapes overboard. Compactors press waste into bales for storage until the ship reaches port. These systems occupy several decks and operate around the clock. They consume a significant portion of the ship's electricity and are strictly regulated by international law. The Marpol Convention sets limits on pollutant concentrations in discharged waters, with violations leading to fines fines in the millions. In 2016, Carnival Corporation paid a $40 million fine for illegal discharge of oil-contaminated water and falsifying records in the oil log. This was followed by several years of judicial oversight. Electricity. This is yet another hidden world. An Oasis-class cruise ship consumes between 60 to 80 megawatts of electrical power. For comparison, this is the energy consumption of a small town with a population of 60,000 to 80,000 people. This power is supplied by 6 diesel generators, each the size of a 2-story building, running on heavy or diesel fuel. They are located deep within the hull, on the lowest decks, behind soundproof bulkheads. Electricity powers everything: the ship's movement, air conditioning, lighting, elevators, kitchens, security systems, navigation, stabilizers, water purification, and refrigeration. Modern cruise ships utilize electric propulsion for their propellers, known as azipod thrusters. These gondolas, equipped with electric motors, are suspended beneath the stern and can rotate 360 degrees. They replace traditional rudders and propeller shafts, allowing the ship to move in any direction, turn on a dime, and dock without tugs. The azipod is an engineering marvel. However, it creates an absolute dependency on electricity. If the generators stop, the ship loses not only light and air conditioning, but also propulsion and control. A complete power loss on a cruise ship is an emergency situation, comparable in severity to a breach in the hull. This is why the power supply system is redundantly designed. 6 generators instead of the 3 needed. An emergency diesel generator on the upper deck above the waterline, capable of providing minimal power for navigation and emergency lighting. Evacuation. This is perhaps the most meticulously concealed yet carefully calculated aspect of a cruise ship. How do you evacuate 6,700 passengers and 2,400 crew members from a ship that is sinking or on fire? In the open ocean, at night, in a storm. Among the passengers are elderly individuals, children, and those with limited mobility. International regulations require that the total capacity of lifeboats and rafts must be at least 125% of the maximum number of people on board. This means that for 9,000 people, there must be space for over 11,000 in lifeboats and on rafts. The surplus is a precaution in case some equipment becomes unavailable due to listing, fire, or damage. But capacity is just the beginning. The key requirement is time. After the evacuation signal, all passengers must be in the lifeboats and lowered into the water within 30 minutes. 30 minutes for 9,000 people, many of whom may be asleep, at the pool, in a restaurant, or at the bar, to make their way to the lifeboat deck, don life jackets, and take their places in the boats. The internal architecture of a cruise liner is meticulously designed as a system of escape routes. The corridors are wide enough to accommodate the flow of people, yet not so wide as to waste space that could be used for cabins. Staircases are plentiful and strategically distributed throughout the length of the ship. Doors are designed to be wide enough for passengers in life jackets, including those in wheelchairs. Signage is illuminated, powered by emergency systems, and visible even in smoke. Every cabin, every corridor, every staircase, every door is not just an architectural feature. It's a component of an evacuation system, crafted based on computer models of crowd movement. These models simulate thousands of scenarios: a fire in the center of the ship, flooding in the aft compartments, a list to one side. Each scenario has its own escape route, its own timing, its own capacity. Consider the Costa Concordia. In 2012, it capsized off the coast of Giglio, resulting in the tragic loss of 32 lives. The ship lay on its side near the shore, and even under these relatively favorable conditions, proximity to land, warm weather, daylight, evacuation descended into chaos. Lifeboats on one side were inaccessible due to the list. Staircases and corridors became impassable. The 30-minute standard for evacuation was repeatedly violated. This incident led to stricter regulations, mandatory evacuation drills before leaving port, enhanced alert systems, new standards for the design of bulkheads and doors. Every disaster is a lesson etched into international conventions with the ink of tragedy. Now let's return to the waterfront. The liner is departing from the port. You perceive it differently. Beneath its pristine white hull lies not a hotel, but a complex machine where every element is at the intersection of conflicting forces. The metacentric height is precisely calibrated to prevent capsizing in storms and to avoid seasickness for 6,000 passengers. The height of the superstructure is maximized for revenue while minimized for maneuverability in the wind. The width of the corridors is sufficient for evacuation, yet minimized to maximize cabin space. The power of the generators is more than adequate for reliability, while being minimized for weight and fuel consumption. This isn't merely about sailing with maximum safety. It's about navigating a corridor where safety, comfort, economy, and physics are balanced with precision down to the meter, degree, and megawatt. And within this corridor lie hidden solutions that serve the passengers while remaining invisible. A fresh air intake system that automatically switches sources based on wind direction, ensuring that exhaust from the ship's funnels doesn't drift onto open decks. Programmable atrium lighting that mimics the natural light cycle, helping passengers maintain a normal sleep rhythm when crossing time zones. Vibration isolation of the decks, multi-layer constructions of steel, rubber, and composites that dampen vibrations from engines operating 2 decks below to imperceptible levels. A passenger in a cabin doesn't hear the 60 megawatt generators running right beneath their feet. This isn't magic, it's engineering, the cost of which is built into the ticket price. And therein lies, I believe, the hidden beauty of the cruise liner. It's not just a floating hotel, it's a constant negotiation between the ocean and comfort. Between the physics that demands stability and the psychology that craves softness. Between safety, which requires steel and bulkheads, and architecture, which calls for open spaces and freedom of movement. Between economics, which seeks the maximum number of cabins, and evacuation regulations that necessitate space for a fleeing crowd. Every time you step into a cabin on a cruise liner, you enter a space whose form and dimensions are dictated not by an interior designer, but by stability equations, crowd movement models, and international maritime safety conventions. And the fact that the cabin feels cozy and comfortable is perhaps the most impressive engineering feat of all. And here's something I've been pondering. We've discussed how a cruise ship battles the waves to ensure comfort, but we haven't touched on the most terrifying scenario that can unfold on board: a fire. Picture this: 9,000 people confined in a tight space, with miles of corridors and synthetic materials that emit toxic smoke. How exactly should a cruise ship's fire suppression system tackle a blaze in an environment where windows can't be opened and the only escape is into the sea? I've created a separate video diving into this topic in detail. You can find it on the channel.